Here we have our DNA. Again, we've taken it, we unwound it. Now here is where we have our topoisomerase. Okay, so I'm trying to keep these from getting dried out. Okay, this guy right here is our topoisomerase, known as gyrase. And remember, it oops, sorry, dropped the marker. It unwound the supercoil, so it's no longer supercoiled. It just was a little, you know, kind of relaxed, like just two rubber bands maybe twisted around each other. Then you have this little pink guy right here. This is the one where it is breaking the bonds between, so here are the bonds, hydrogen bonds between our base pairs. Okay, this guy right here, if you can see it, I hope you can see it, little triangle guy, he is helicase. Okay, so that's our helicase right there. That has further unwound. So again, we went from being unwound to now we're, you know, completely open in that area. That's why we have this area here. Okay, the little red ones are the SSBPs. So those are the single strand of binding proteins. Their purpose is to keep, you know, it's like, again, a rubber band. If you let it go, it just wants to go back, right? If you're stretching it, it wants to go back. So the SSBPs prevent the strands from re-annealing. We don't want them to go back to each other. We don't want the hydrogen bonds to come back. We want them to stay open. Okay, where we're at right now, and I'm just going to put it on this side, but both of these have it. This area here is called a replication fork. And this whole area here is a replication bubble. Okay, so, and it does, it looks like a bubble. All right, so we have a replication fork, and each bubble has two forks. All right, and this is where we do not have our hydrogen bonds in between there. Okay, so we have at this point now and this is all going on. I mean, this is all happening kind of simultaneously. It's not that it happens one at a time. I'm just drawing it that way. So I'm going to use orange, I think. So our primase comes along. Now, mind you, I've marked it out. So, oh, actually, I'm sorry. I have mine upside down. Where'd that marker go? Oh my goodness. Oh, it's right here. I am sorry because I actually did not follow my own strand. S3. Oops. Oh, come on. I want that to be my 5'. I'm sorry. I want this to be my 5' and that to be my 3'. I apologize greatly. Make sure I did that. Yep. And I'm going to, matter of fact, have this come over there. Okay. Okay, I'm going to leave that alone since that was my fault. 5', 3'. Okay. So I want to make more strands of whatever's going on in here. So first things first, I'm going to take an RNA or primase, and what that is about 100 to 200 bases, and it's kind of a standard. And this is our primase, and it lays down RNA. So we call it DNA primase because this is our primer for DNA replication. And this is going to lay down, oops, a little RNA. Sorry, I'm sitting down. I have all these things in my lap. Sorry, it's going to lay down RNA, again, roughly 150 to 200 BPs, or base pairs. Okay, so that's all that is. All right, so far we have gyrase, which is our topoisomerase. We have helicase, which is to unwind and definitely unzip and get rid of those hydrogen bonds. We have SSBPs, our single-stranded binding proteins. That's going to keep open our replication bubble. We have 2 replication forks, and we want to go ahead and start adding our nucleotides in. So we've already started with the primer. Here's the thing. The primer, now follow my hand, okay? The primer, I remember I said this was important because I wanted to change my numbers. So here's my primer, and this primer goes to 3' right here. All right, so this is a 3' strand. So if I write it, I'm gonna then put it here so you see it a little bit more. It's a little more familiar now. Okay, so this 3' goes to this strand right here. This is important because this is our leading strand. And then here's my 5' on here. Remember, what the 3' is, all it's saying is my sugar has not yet joined its hydroxyl group there at the 3 carbon or 3rd carbon, okay? Because remember, this one we've now kind of opened it up. All right, so I can add bases, and I do that by adding a base that is available at its 5'. So that's why when we talk about adding 5 to 3, I'm going from this guy here, and I'm going to add my bases. And because I want to do the opposite strands, I'm going to add a 5' to a 3'. So what it means is I'm going to add something that is not bonded yet. Remember, it has my phosphate group here. Remember, they are anti-parallel. Okay, so I can connect my phosphate group. Sorry, it's a little backwards, upside down, but that means I can attach my 5 carbon phosphate area, right? So that's the end that's going to get connected. So we start adding in nucleotides, and so let's say we have A and we have T, C, G, and they're just kind of floating around. Whatever is on this side, again, whatever is over here, I'm just going to do T, A. Remember, these are anti-parallel. Oops. Okay, I'm going to start adding. Let me get this out of the way. It's a little messy. Okay, so now hopefully you understand a little bit more with why we're adding 3' and what it means to add 5'. All right, so now we're just going to add, and what I'm going to do is, again, I'm giving you kind of the illustrated version, is the nucleotide that comes on, that is 5', is going to be the opposite to my 3' end. Okay, so right there. Understand, now look, these are identical. All right, so notice now I have 1 copy of my other strand. Here's where the problem is. Okay, with all this going on at the same time, you have this bottom strand here, 3' to 5'. And the thing is, nucleotides only add, going from that 3 to 5, they only add 5. They add on from their 5 to 3' end, okay? So what it means is I can only add 5' to 3' going in this direction, all right? Because this is 5' and 3', remember, I can only add 5 going in that direction, okay? So what has to happen? Well, unfortunately, this is fortunately, this just continues. It's a natural flow. It just keeps on going, you know, nothing big. So this is our leading strand. All right, this is our leading strand. This side here is our lagging. Okay, this is our lagging strand. And again, I really hope you can see this, because this is my first time doing this, by the way. Okay. And I am not going to edit. I mean, I'll cut off where my son probably came in here and there. But for the most part, I'm not going to edit. So this is what you get. Okay, so here's my 3' to 5'. I can't add going in from my 3 to 5, okay? So what has to happen is there's a fragment. Now remember, oops, where'd my orange go? Uh-oh, I lost my orange. Nope, here it is. Sorry. Remember, we're going to lay down the RNA primer, except I'm going in that direction. Okay, so I'm laying down my RNA primer. Remember the orange here? I'm just going to do this here. This is our primer. Okay, so you kind of remember really quick. This is our primer. And unfortunately, it can only add because it's forcing it to go in the opposite direction. It doesn't want it. I mean, it really doesn't want to go, but it has to go this way. So by forcing it, it can only go a little bit and then it stops. So it can only add C, T, T, A, and then it stops. Okay? Now, that stopping point, this guy right here, all that happened right here, we give it the name Okazaki. Okay? It's an Okazaki fragment. It was named after the guy that identified it. I couldn't even say his first name if I tried. It starts with a T. So we'll just call him T. Okazaki. Okay. But he identified that this is how it works on this side because it cannot go. It can't add on 3 to 5. It has to add on 5 to 3. Okay. So anyway, it'll do the primer, adds what's called an Okazaki fragment, and then another primer. And then let's say here's our Okazaki fragment. Okay. And it's going to do this the same time that this is happening. This is all happening at the same time. Okay. Remember, this is our leading strand. This is smoothly adding our nucleotide bases in and pairing up. And this is our lagging strand. It's lagging behind. It's taking a little longer. Well, it's not taking a little longer because it's happening simultaneously. But again, it lags in a sense because it has to have these fragments in here. And what happens is these fragments, again, oops, I'm running out of colors here. Hold on a second. Let's go back to green. These fragments now have to get, at some point, joined together. We have to remove the primer and join together. Okay? Now, understand that RNA, the DNA polymerase 3 is, again, a protein, an enzyme that is adding these nucleotides in. All right, so DNA poly 3 is adding them in. DNA poly 1 is going to go back and check everything and proofread it and make sure that everything matched up, that there weren't any errors going on. Okay, so DNA polymerase 3 is going to add the nucleotides, and DNA poly 1 is going to go and just check everything and make sure it's okay. All right. Well, anyway, we now have these fragments here, and we need to pull them together. So we are going to kind of glue them together, and by doing that, we're then going to remove the primers. And we're going to use what's called ligase. And the ligase is going to glue together our Okazaki fragments. It's kind of sealing in what's missing because there's these little, sections of nothing. And so what the ligase does is it kind of adds just a couple nucleotides to fit this section, and then that way it's now all together there. And we now have a full strand. And then we have the last one, we have exonuclease. Comes in, saves the day, right? But no, it removes the primers. Can you see this down here? I hope so. Oh, good. It's like right at the bottom. Okay. and it's going to take away those primers here and get them out of the picture, and you now have your Okazaki fragments that are connected together. Okay. I hope I addressed the question of Okazaki fragments. I'm hoping I helped a little bit with the enzymes that you need to know. I don't think before I mentioned exonuclease, but I do want you to know that one. I think that's it. So let me know how this worked, since this is new and we might be doing this. All right. Or let me know how you want me to stand or sit or whatever, because right now I'm sitting. This was tough, kind of, without letting this fall. Well, okay.